Hello students, here in this presentation we can view how by applying molecular orbital theory the formation of 6 metal ligand sigma bonds can be explained in octahedral complex. Well, you are aware that there is a set of assumptions on the basis of which one can construct the molecular orbital energy level diagram for metal ligand complex, that is of course in octahedral complex. Of course, keep it in mind that metal ion belongs to 3D or 4D or 5D transition series. Now, in the second we can see the rules for constructing molecular orbital energy level diagrams. Now here total 15 orbitals, that is 9 from metal ion and 6 from 6 ligands are available for molecular orbital formation. There are 5 d orbitals, 1 s and 3 p. So total becomes 5 plus 1 plus 3, that is 9. So 9 orbitals are made available from the metal. Before approaching the metal orbitals, field ligand orbitals overlap with each other first. So linear overlapping of ligand orbital take place and that results in 6 ligand group orbitals. So these ligand group orbitals are then ready to approach the metal orbitals. Of course, they will approach along the axis and form one bonding and one antibonding molecular orbital each. Symmetrical overlap is prevailing here. So those having lobes directed along the axis, they will undergo direct overlapping and they result in sigma molecular orbitals. Whereas dxy, z and dxz orbitals, they do not take part in sigma bonding. Now coming to this slide where we have described the metal orbitals, how they are classified based on their symmetry classes. We can see here that the s orbital, which is labeled as A1G, the 3p orbitals, namely px, py, pz, they are labeled as T1u, that is triply degenerate, dz square and dx square minus y square labeled as EG, that is doubly degenerate orbitals. dxy, dyz and dxz, this set of orbitals is labeled as T2g. Remember, they remain as non-bonding. 4s and 4p, they show greater extent of overlapping. Now here one has to note that the prominent feature is extent of overlapping is different for different set of orbitals. So 4s and 4p orbitals will show greater extent of overlapping compared to the 3d orbitals, and therefore the energy gap between the bonding and antibonding molecular orbitals for 4s and 4p orbital is always quite large, larger than that of 3d orbitals. Here, this is a general molecular orbital diagram in front of you. You can view that we have drawn the energy arrow. So first step is the drawing energy arrow. Then extreme left we are drawing metal orbitals. Extreme right we are drawing 6 symmetry orbitals, that is sigma symmetry orbitals. They are labeled as ligand orbitals. Now here the 3d orbitals we have labeled as per the symmetry classification, that is Eg plus T2g, total 5 orbitals. A1G set, that is only single orbital, and the next energy level, that is the top energy level, is 4p labeled as T1u. Now here the 2 Eg orbitals, they will overlap with 2 ligand group orbitals and they will form Eg sigma and Eg star, that is anti-bonding orbital. So we can see in the diagram also sigma Eg, that is bonding, and sigma star Eg, that is anti-bonding. Now ligand or group orbitals of matching symmetry always result in the sigma and sigma star, that is bonding and anti-bonding orbital. Now here we can see that next level there is single orbital A1G. It will overlap with again single orbital, that is from ligand group orbital, and that will result in the big energy gap between A1G sigma. You can see the lowest bonding molecular orbital, and sigma star A1G, that is anti-bonding A1G orbital. The top level, that is 4p orbital, which is T1U. There are 3 orbitals and they will overlap with remaining 3 ligand group orbitals and get split up into 3 sigma T1U and sigma star T1U, that is bonding T1U and anti-bonding T1U orbitals. Now here we can see the filling of electron. It is starting from the lowest A1G set of orbital, that is the sigma A1G bonding, then next T1U, next filling of Eg. So all these levels are completely filled. Next is the T2G. Now T2G remaining as the non-bonding. The electrons now here have the opportunity either to pair up or to go to the higher energy level, and it will strictly depend upon the strength of the ligand, that is ligand field strength. Here ligand is fluorine, which is a weaker ligand. Being a weaker ligand, it will be having the lower field strength, therefore the splitting of Eg star and T2G is small. We can show this with the help of delta O. Delta O denotes that the energy gap between T2G and Eg star, it is small. It is small because the ligand strength is small. Now when the ligand field strength is small, the electrons prefer to jump to the higher energy level, and therefore they occupy Eg star, that is anti-bonding energy level, rather than pairing with the lower T2G. Now what is the result of this? The result of this is we can view that there are unpaired electrons present in T2G and Eg star. As the number of unpaired electrons are more in this complex, we can call this complex as a high spin complex or spin free complex. And of course one can predict the magnetic behavior of this complex. There are present unpaired electrons, so that will make the complex paramagnetic. Now is the diagram for hexacyanoferrate 3 ion. Now in examination there may be tricky questions, that is a comparative study of hexafluoroferrate and hexacyanoferrate. Now the only difference one can make out here is the ligand field strength. Cyanide ions, these are producing stronger ligand field, which will result in the larger energy gap between T2G and Eg star. When the energy gap is higher, then the electrons will prefer to pair up in the lower energy level than to jump to the higher energy level, which is quite evident from this diagram. Comparative study shows that rest all the things being same, the only difference is filling of the electrons at the last stage, that is in T2G and Eg star. Here as delta O, that is energy gap being high, the electrons prefer to pair up in the T2G level, and therefore no electron goes to the higher Eg star. Please have a careful look at this diagram. and therefore we can conclude that the number of unpaired electron is only 1. So this complex becomes spin paired or low spin complex. And of course magnetic, there is an unpaired electron, so it is paramagnetic, but the complex we can call it as a low spin complex because maximum electrons are paired.